This video is about the 4 Denavit Hartenberg parameters. The context of this video, of these parameters, is that we're trying to find the homogeneous transformation matrix from one frame, which we'll call n-1, to the frame immediately after it, which we will call frame n. Previously, we had learned that these matrices were represented by a capital letter A, with the frame that we're going to as written as a subscript. This means the homogeneous transformation matrix from frame n-1 to frame n. In the Denavit-Hartenberg method, we will also use this same notation, and we're going to be looking at the 4 parameters that are necessary to define AN, the homogeneous transformation matrix from frame n-1 to frame n. These 4 parameters include 2 rotation parameters and 2 displacement parameters. The 2 rotation parameters are called theta and alpha. The theta parameter is defined as the rotation around axis Zn-1, while the alpha parameter is defined as the rotation around axis Xn. The rotation around Zn-1, theta, is the joint variable. If joint n-1 is revolute. Alpha n, the rotation around xn, is the rotation, or the angle, that is, between axis Zn and axis Zn-1 measured around the axis xn. For example, let's suppose that you have the 2 joint manipulator shown here in this kinematic diagram. Notice that I drew these 2 joints so that there is an offset, both in the z0 direction and, as currently shown, in the x0 direction. Let's find the theta and alpha parameters that go from frame 0 to frame 1. Oftentimes, the way that we write the values of these parameters is by making a table. We're going to find the theta and the alpha parameters, and in this case we're only going to be able to find them for frame 1 because I've only shown 2 joints, joint 0 and joint 1. If I had more joints, we would be able to find the parameters for frame 1, frame 2, and so forth. This column that I've shown here is the value of n, the frame that we are going to for our homogeneous transformation matrix. So we're going to find the parameters theta and alpha for the homogeneous transformation matrix from frame 0 to frame 1. Theta 1 is the rotation around Zn-1, which would be Z0, shown here. And we know that if the joint 0 is revolute, then theta n is the joint variable. And so here, theta 1, we can simply write that as being theta 1, where theta 1 is this joint variable. Alpha is the rotation around xn, that is, the rotation around x1, that gives the angle between Zn, that is Z1, and Zn-1. The angle alpha 1 is going to be 90 degrees. Alpha N is defined as the rotation around xn, that is, in this case, x1, and that is the angle between zn, z1, and zn minus 1, or z0. In other words, alpha 1 is the angle that we would have to rotate zn minus 1 to get it to match z1 by rotating it around x1. The positive direction of rotation around x1 is this direction. I would have to rotate z0 in that direction 90 degrees in order to get it to match z1. And that's how I know that alpha 1 is 90 degrees. Now, let's look at the two displacement parameters. The two displacement parameters are called d and r. D is defined as the displacement between the two frames along the z minus 1 axis. Rn is defined as the displacement between the two frames along the xn axis. Let's see what these two parameters are for our example kinematic diagram. Note that just like theta n was the joint variable if the joint is revolute, dn is the joint variable if the joint is prismatic. In our example, we don't have any prismatic joints, but in the section of these videos where I'm showing complete examples, we will do some examples with prismatic joints. In order to fill in these displacement variables, we need to label our link lengths. And I'll label these just as we've learned previously, by using the lowercase letter a and labeling each link length. D1 is defined as the displacement between the two coordinate frames along the axis zn minus 1. The displacement between frame 0 and frame 1 along the axis z0 is a1. So here, the d parameter is equal to a1. The r parameter is defined as the displacement along xn. xn here is x1. The displacement between frame 0 and frame 1 along the axis x1 is equal to a2. So the r parameter here is a2. These four parameters, theta, alpha, d, and r, are the only parameters we need to find the complete homogeneous transformation matrix between any two frames. Once we've found these four parameters, we find the homogeneous transformation matrix by plugging the numbers into a standard matrix. I'm now going to show you what that standard matrix looks like. In the homogeneous transformation matrix that I've shown here, I've used the letters S and C to represent the sine and the cosine of the angle parameters. Note that the only variables in this matrix are the four parameters that we've already identified. We have theta appearing many times in this matrix. We also have the variable alpha. And we have several occurrences of the displacement variable r, and a single occurrence of the variable d. So once we have these four variables identified, finding the homogeneous transformation matrix does not require any matrix multiplication as was required in the method that we learned previously. We can simply plug in those four variables to get the homogeneous transformation matrix directly. Note that the use of this method relies upon having defined all of the axes, all of the coordinate frames, according to specific rules that are laid out in the video on defining coordinate axes. As long as you've defined the coordinate axes according to the Denavit-Hartenberg rules, you can use these four parameters to directly find the homogeneous transformation matrix.